What is space? What is mass? These fundamental questions have captivated philosophers and scientists for centuries. Is space merely an empty stage where the drama of the cosmos unfolds, or does it have properties of its own, playing an active role in the grand cosmic play? And what of mass, the seemingly solid stuff that makes up our world? How does it interact with the fabric of space itself? The journey to unravel these mysteries takes us on a thrilling adventure through the history of physics. Sir Isaac Newton, a towering figure in the scientific revolution, envisioned space as an absolute and unchanging framework. His ideas laid the groundwork for classical mechanics, a field that would dominate scientific thought for centuries. Newton's conception of space was akin to a vast, empty stage, a rigid and unalterable backdrop against which the drama of the universe unfolded. This stage was not influenced by the objects within it, rather it provided a fixed reference point for all motion and rest. Like a rigid stage upon which objects move, space, in Newton's view, provided a fixed reference for measuring motion and rest. This concept was revolutionary because it allowed scientists to describe the motion of objects with unprecedented precision. By treating space as an absolute entity, Newton could formulate his laws of motion, which describe how objects move and interact. These laws became the cornerstone of classical physics, enabling the prediction of planetary orbits and the behavior of falling objects on Earth. Mass, in this picture, exerted a force we call gravity, attracting other massive objects across the cosmic expanse. Newton's law of universal gravitation posited that every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant equation explained not only the motion of planets around the Sun, but also the tides, the trajectories of comets, and the behavior of objects on Earth. This force, according to Newton's law of universal gravitation, determined the motion of planets, stars, and galaxies. It provided a unified explanation for a wide range of phenomena, from the falling of an apple to the orbits of celestial bodies. Newton's insights allowed humanity to understand the universe in a new way, revealing a cosmos governed by predictable and consistent laws. His work laid the foundation for future scientific advancements and inspired generations of scientists to explore the mysteries of the universe. While revolutionary in its time, Newton's framework left some profound questions unanswered. For instance, what was the nature of the force of gravity itself? How could it act instantaneously over vast distances without any apparent medium? These questions puzzled scientists for centuries and hinted at the limitations of Newtonian mechanics. Despite its success in explaining many aspects of the physical world, Newton's theory could not account for certain anomalies, such as the precise orbit of Mercury or the bending of light by gravity. What exactly was gravity, and how did it act over vast distances? These questions would eventually lead to the development of new theories and a deeper understanding of the universe. The quest to answer these questions paved the way for the revolutionary ideas of Albert Einstein and the theory of general relativity, which would transform our understanding of space, time, and gravity. Newton's work, while not the final word, was a crucial step in the ongoing journey to comprehend the cosmos. Enter Albert Einstein, a revolutionary thinker who dared to challenge the very foundation of our understanding of space and time. In his groundbreaking theory of general relativity, Einstein proposed that space and time are not separate entities, but rather interwoven threads in a dynamic fabric he called spacetime. This revolutionary concept forever changed our view of the cosmos. Imagine a trampoline as a model for spacetime. Now, picture placing a bowling ball in the center of the trampoline. The ball causes the fabric to sag, creating a dip. This is analogous to how massive objects warp the fabric of spacetime. Gravity, according to Einstein, was not a force acting at a distance, but rather a manifestation of the curvature of spacetime caused by the presence of mass and energy. Objects moving in this curved spacetime follow paths determined by its geometry. just as a marble rolling on the trampoline would follow a curved path around the bowling ball. Section 5. Ripples in the fabric gravitational waves. One of the most mind-boggling predictions of Einstein's theory was the existence of gravitational waves, ripples in the fabric of space-time that travel at the speed of light. These waves are not just theoretical constructs, they are real phenomena that can be observed and measured. Imagine space-time as a vast, flexible sheet. When massive objects like stars or black holes move, they create disturbances in this sheet, sending out waves that propagate through the universe. These waves are generated when massive objects accelerate, like ripples spreading from a stone thrown into a pond. The more massive the object and the more violent the motion, the stronger the gravitational waves. For instance, when two black holes spiral towards each other and eventually collide, they send out powerful gravitational waves that can be detected billions of light years away. The detection of gravitational waves, a century after Einstein's prediction, opened a new window into the cosmos. This monumental achievement was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO's incredibly sensitive instruments can detect the minuscule distortions in space-time caused by passing gravitational waves, allowing scientists to observe events that were previously invisible, allowing us to study some of the most cataclysmic events in the universe, such as supernova explosions and gamma-ray bursts. These events release enormous amounts of energy and can tell us a great deal about the life cycles of stars and the dynamics of the universe, such as the collisions of black holes and neutron stars. These collisions are not only spectacular but also incredibly informative. They provide insights into the nature of gravity, the behavior of matter under extreme conditions, and the fundamental laws of physics. By studying gravitational waves, we are not just learning about distant cosmic events, we are also gaining a deeper understanding of the universe itself. Section 6. The quantum jitterbug. Empty space isn't so empty. While general relativity beautifully describes the universe on the grand scale of stars and galaxies, it falls short when we zoom into the microscopic realm. The vastness of space, with its sprawling galaxies and twinkling stars, is governed by the elegant equations of Einstein's theory. These equations predict the motion of planets, the bending of light around massive objects, and the expansion of the universe itself. However, the world of the very small, ruled by quantum mechanics, presents a different set of rules. Here, particles behave in ways that defy our everyday experiences. They can exist in multiple states at once, teleport across space, and even influence each other instantaneously over vast distances, a phenomenon known as quantum entanglement. One of the most intriguing concepts in quantum mechanics is that of quantum fluctuations. These are temporary changes in the amount of energy in a point in space, as predicted by Heisenberg's uncertainty principle. This principle states that we can never simultaneously know the exact position and momentum of a particle. Imagine the fabric of space-time as not a smooth trampoline, but rather a constantly fluctuating surface, like the surface of a boiling pot of water. These fluctuations are not just theoretical, they have real, measurable effects. For instance, they contribute to the Casimir effect, where two uncharged metallic plates placed close to each other in a vacuum experience an attractive force due to the quantum fluctuations between them. Bubbling with virtual particles popping in and out of existence, these particles are called virtual because they exist for such a short time that they cannot be directly observed. Yet their presence can be inferred from their effects on other particles and fields. These fluctuations, known as vacuum energy, suggest that even empty space is not truly empty. Instead, it is filled with a seething sea of quantum activity. This vacuum energy is thought to be responsible for the mysterious force known as dark energy, which is driving the accelerated expansion of the universe, but rather a seething sea of quantum activity. This realization has profound implications for our understanding of the universe. It suggests that the vacuum of space is a dynamic, ever-changing entity teeming with energy and potential. As we continue to explore the quantum realm, we may uncover even more surprising and fundamental truths about the nature of reality itself. Section 7. A cosmic pas de deux. Space and mass intertwined. The interplay between space and mass is a delicate and dynamic dance. Mass warps spacetime, dictating how objects move under the influence of gravity. But the curvature of spacetime, in turn, influences the distribution and motion of mass and energy. This intricate relationship is at the heart of our understanding of the evolution of the universe.